Right, in question number 10, you've got a diagram that tells us that BC is parallel to DE. You can see that on the diagram. Part A, you've got to prove that the triangle ABC is similar to triangle ADE. ABC is the big one, ADE is the little one at the top. And to prove similarity, you have to prove that all of the angles are the same. If something's similar to something else, it is the same shape, but it has different lengths, different dimensions. So, to do the first bit, if we look at this angle here, DAE, angle DAE, we can say that that is equal to angle BAC, and that's because it's in common in both triangles. It is in the small one, it is in the big one, so we can say it's in common. Okay, this notation is useful to use. It's just, this is angle DAE, this is angle BAC. Now, we need to prove that all the angles are the same, so this angle and this angle are going to be the same, but why? So AED, angle AED, is equal to ACB. And that's because they are, you've got the parallel lines, they are corresponding to each other. That's what you can say there. So they are corresponding angles, corresponding it will do. And then we've got this same reason, you've got angle ADE is equal to ABC, and that's because they are corresponding as well. So there's our three reasons, and we can say that's therefore ABC is similar to ADE. 3 marks. Right, B, calculate the length of AC. Now this is where it's useful to think about these two triangles separately. So you could even draw the small one and the big one out as a couple of separate diagrams away from each other. ADE and ABC, just label the sides. Really bad triangle there, I know, but we've got 4 centimeters for the base of that one and 12 centimeters for the base of the larger one. And you've got this 5.8 centimeters measurement for the length of A to E. We've got to calculate this length here, AC. We don't know what that is. But we can work it out because we know they're similar to each other. Therefore, there must be a scale factor involved in this enlargement. And that scale factor is found, and we're going to call it the linear scale factor, because we can find it by doing 12 divided by 4. We can see that that gives us 3. So the linear scale factor is 3. This length is 3 times longer than this length, which means that this length has to be 3 times longer than this length. And so we're going to be able to work out that length now. I'm just going to multiply 5.8 by 3. So 5.8 multiplied by 3. If you do 5 times 3, you get 15. So I'm going to write this separately. 5 times 3, you get 15. And you do 0.8 times 3, you get 2.4. So you add those together, you're going to get 17.4 centimeters. And there's your answer for the length of A to C. It could be a little bit more complicated, E to C. That's not really much harder, is it? You just take away the length AE, and you've got this length left over. Pretty simple. Right. Part C, you've got to find the ratio of the area of the quadrilateral DBCE to the area of triangle ABC. So that is, they're throwing a little bit of a curveball in here because you've got the quadrilateral that we hadn't previously thought about because we were just dealing with the fact of the similar triangles. We've got the quadrilateral, and I'm going to draw that there. So we've got D, E, B, and C for the quadrilateral, and I'm just going to faintly draw the rest of that triangle in there. Okay, but we've got D, B, C, E for our quadrilateral, and we've got the triangle ABC. I'll draw that on the other side there, which is just the big triangle which we've drawn previously, ABC. Okay, and then I'm just going to draw that faint line in there. So we've got, exactly the same thing drawn on both sides, but I'm just showing you That's what they're talking about with the quadrilateral. That's what they're talking about with the big triangle ABC. When we need to work out what the ratio of the areas are. Okay, so we know the linear scale factor to be 3. We worked that out in the previous question. Now, to work out an area scale factor, how many times the area of something is, we can't work out the area of these shapes. We've got no perpendicular heights for the trapezium or for the triangle, so we can't work out what their heights, what their areas are. So all we can do is work with the fact that we know that this shape, this triangle, is 3 times bigger than this little triangle, right? So if we make the area of this little triangle 1, right, 1 unit squared, then we're going to say that this is 3 times bigger. Now you need to know that the linear scale factor squared equals the area scale factor. That's the fact you need to know. Equally, the linear scale factor cubed equals the volume scale factor. So if we use that fact there, if this was 1 unit squared, this little triangle here, this faint one at the top, this faint one at the top here, then and this was the area, we were calculating the area, that'd be 1 squared, right? 1 squared is 1, that'd be worth 1. And this is 3 times bigger, so that would be 3 squared. So this whole thing would be worth 9 units. 3 squared. 3 squared equals 9. 1 squared equals 1, right? Now you can see if this is 1 and this whole thing is 9, then this must be 8, right? So the area, so we're not saying that's the area, we're saying the ratio of the areas is going to be quadrilateral 8 and triangle, big triangle, 9. Really complicated question, actually. So 8 to 9 would be your answer for that question. I'm trying to think of a nicer way of trying to explain that one. Can't really think of a nicer way to give you an answer to that question just yet. If I do, I'll come up with another video for you.